Hello, everybody, and welcome to the Python Exchange event for January 2023. We have a very large panel set up for you today, as well as a fantastic guest panelist. I don't want to delay too much further, but I want to note a couple of things before we get started. Note that these sessions are recorded, and a recording will be available after the event. We'll be sending to you on email, and you can also find it on the Python Exchange website. Do note that if you have any questions, please do make use of the discussion widget and the Q&A widget, and all of the panelists will be monitoring both of those during the presentation, during the prepared remarks, as well as during the Q&A section, and would be more than happy to answer those questions. If you happen to have questions, please don't feel like you have to limit those for just our guest panelists. In fact, if you have any questions at all about anything that any of our panelists can help you with, please feel free to make use of that discussion or that Q&A widget and ask, hey, Dan Allen, what about this? Hey, Jim Pivarsky, what about that? Hey, Ross, what about this? We're here to be a resource for you to improve your use of Python, because the goal of this group is to see Python succeed within the national labs and associated facilities. Do note that if you work at a classified site, please do not share any information that you are not authorized to share, either in the Q&A widget, in the discussion widget. Use your best judgment and do pay attention to the policies as appropriate and as dictated by your facility. And so with that said, I'm going to share my screen in just a moment and introduce you to our panelists for today's event. Today, we are joined by a number of host panelists, as well as a very special guest panelist. We're going to have some representation not only from the core Python language, but also from the Steering Council, as well as an expert in topics such as instrumentation and optimization of Python code. And so behind me, you'll see my screen. I'll, of course, hide in the corner here, and I'll give each one of our host and guest panelists an opportunity to introduce themselves. I'll set the format for them. Of course, if you have any questions after this event is over, or if you want a copy of the recording, please do visit our website, meetup.doepy.org. But starting off with our host panelists, each one of our host panelists down the line will introduce themselves. I'm James Powell. I'm from NumFocus. I serve as the chairman of the board of directors, and they'll share with us in just one sentence the kinds of questions that they would be more than happy to answer for you in the Q&A widget, in the discussion widget. Any of the questions they're here to answer for you. And so if you have questions of the form, why do they call it a tensor? Isn't a tensor just a fancy word for a vector? I'd be more than happy to answer a question like that for you, or to answer questions about projects in the open source scientific computing community that are fiscally sponsored by NumFocus. How do you join one of those projects? How do you contribute to one of those projects? How do you make your project one of those? Those are the kinds of questions I'd love to answer for you. Next up, we have Dan Allen from Brookhaven National Laboratory. Dan, what kind of questions would you love to answer for people today?
Sure. I'd love to talk about building communities across the national labs to sort out what parts of the software we can share and what parts we need to specialize on.
Fantastic. Next, we have Tom Caswell from Brookhaven National Lab.
Hi, I'm Tom Caswell. I guess I'm happy to answer questions about matplotlib visualization and how to maintain a large-scale project in the sci-fi space.
Next, we have Matthew Carbone, also from Brookhaven National Lab, but from a slightly different part of Brookhaven. If you'd like to clarify the distinction there, Matthew, in addition to telling us what kind of questions you're here to answer.
Sure. I'm from the Computational Science Initiative at Brookhaven National Lab. I'm primarily a researcher. I do a lot of machine learning work, a lot of software stuff, physics. So anything related to numerical scientific computing, I can definitely help with.
Fantastic. We're also joined by Ross Barnowski, who was a previous guest panelist here representing Caltech. Ross, what kind of questions would you love to answer for our audience members today?
Hi, I'm happy to answer anything. To be completely honest, I think I just clicked on the wrong link. I'm mostly here to hear Pablo, but I'm happy to answer any question that I can. Currently work on NumPy and NetworkX.
Oh, fantastic. So questions about NumPy and NetworkX. Next up, we have Jim Pivarsky, who is one of our previous guest panelists and a real hotshot when it comes to, I believe, high energy physics. Jim, you're here representing Princeton University. What kind of questions would you love to answer for people today?
I also came primarily intending to listen, but considering the change of plans, I will. I'd like to ask. I'd like to talk about Numba, the Numba project, which I'm not a member of, but I work closely with it with my work on Awkward Array. And the reason that I would like to focus on that here is because there are some issues between Numba and the core development that I'd like to see fixed.
Oh, fantastic. So if people have questions about how they can use Numba in their work, I'm sure you'll be a great resource for them. Next up, we have Daniel Margala representing NERSC. Daniel, what kind of questions would you love to answer for folks?
Sure. Yeah, so I'm at NERSC, and one of my primary roles at NERSC is to support scientific Python users on our new GPU supercomputer Perlmutter. And so I'd be happy to answer any questions kind of related to supporting the variety of packages in the Python ecosystem, and especially getting those to work on the large distributed GPU system.
Fantastic. And I think we're missing just one name from our list. Jan, I noticed that you were able to join us just at the last minute today. Jan Janssen from Los Alamos National Labs. Jan, would you like to briefly introduce yourself and tell people the kinds of questions that you could help them with today?
Sure. Yeah, my name is Jan. I come from the Los Alamos National Lab. I do workflows in Python, and I contributed quite a lot to the Conda Forge community. So roughly 500 packages, and I'm close to reaching 100 million downloads with these 500 packages. So they get some popularity in the material science community, and I guess for us it was a big step to no longer having to compile the software and get all the dependencies, but be able to insert simply. So maybe that's something we can transfer to other national labs or other communities of science to really embrace Conda Forge there.
Fantastic. We have a great set of host panelists for you today, representing all sorts of different use cases with Python throughout national labs, as well as associated facilities. But I am very happy to introduce you today to our guest panelist, Pablo, who will be representing the Python Steering Council and is also a very well-established core developer. Pablo, what kind of questions would you love to answer for people today as part of our Q&A section?
Hey, hi everyone. So I would love to talk anything about Python and Python the language and like what things, how like the governance model work, how we add features to the language, but also I would love to discuss anything that can help, building bridges between different communities of library maintainers and users and the Python core team. As normally we seem like this mysterious group of people that drive the language, but we always like to be in contact with the community. So any question regarding that, I will be happy to answer. And additionally, I would love to talk about the difference between a tensor and a multidimensional array. I think that will be a fantastic topic.
Fantastic. Now, I noticed when looking at our list of attendees that I see a couple of names that have been to many of our previous events. We are always looking for new host panelists. Please do reach out to us and let us know if you'd love to be a part of the discussion on stage with the rest of us, beyond just what you can do within that discussion widget and that chat widget. We would love to have you. But with that said, let us start with our very first activity for today's session. As with all of these calls, we like to start with a little bit of a coding activity. Then we'll go into the prepared remarks from Pablo. Then we'll open it up for some generalized Q&A. And our coding activity for this event, well, we're going to start off pretty easy with something that I think will be pretty straightforward for all of our panels to do, a nice little short activity. We have some code that was written by a scientist to solve a very, very, very small problem. And they come to you and they say, could you review my code? And they don't want you to hear, this is terrible, rewrite it from scratch. They want to hear some targeted, concrete material feedback, and they want you to tell them why it even matters. And so I will present you with a very small snippet of code, the inputs that it takes and the outputs. It's just a very short 30-line analysis, and we would like our panelists to tell us, how could that code be improved? What mistakes may have been made? What bad habits might be present in that code? And how can we justify that beyond just saying this is more elegant, this is how a proper programmer would write it? How can we really make that something that a scientist will listen to and appreciate? To give you a sense of what the code is all about, let's imagine that we have some scientists and they manage some devices. And those devices have some counters associated. We just have some numeric values. And so they have some input data that looks like what you see on the left-hand side of the screen. Device 1, device 2, and device 3. And for each one of these devices, there's some measuring device, some counter, whatever it might be. For device 1, ABC was measured at 1, 2, 3. DEF was measured at 4, 5, 6. For device 2, we have these measurements for ABC and XYZ. For device 3, we have ABC, GHI, XYZ with those particular values. Now, I'd like to pause here for a moment. Does anybody ever have any experience looking at any sort of input data that looks kind of like this? That you could squint and say, you know, that's kind of like something maybe one of my scientists has looked at? Please jump on audio and let us know in case that'll give some proper color for this. Well, I'll assume that it's maybe just a little bit general enough that we all can get a good sense of that. Here's what the scientist wants to do. They want to take this input data and they want to generate a report that you can see on the right-hand side. They want to just sum up what all the ABC values across all the devices are, all the DEF values across all the devices, all the GHI values, all the XYZ. They just want to sum up the counters. And so whatever the case of whatever these represent may be, that's what they want to do. Here is the code they wrote. Now you might have to squint just very slightly to take a look at it. I'll double share my screen for our panelists just in case that'll help them to see this code. But I'd like to give our panelists just a couple of moments to take a look at this code and then to give our scientist some feedback in terms of what did they do right, what did they do wrong. Now I promise you, the inputs for the code look exactly like what I showed you on the previous screen, and the outputs of this code look exactly like what I showed you on the previous screen. There's nothing surprising here, except maybe how the code happened to have been written. What did they do right? What did they do wrong? What could they have done right? I'll open it up for our panelists as they see fit to jump in and tell us what they think.
I'll jump on one. Seems like there's an opportunity to make the file name that it runs on configurable. If it's usually called hardware CSV, maybe that would be a better default value to run a report than a hard-coded value.
Absolutely. And I think that's a very, very direct thing that you could motivate for them. You could say, well, what if you happen to get a different file name? Now, on the other end, Dan, should this function just print out the total values?
Return from the function and then print in the main block.
Very
and by the way, that's the cutest way I've ever seen a main block written. I don't know if I've ever seen that before.
Matt, you know, these scientists are very resourceful, so they find something that works and they jump on it. Does anybody have any comments about some of the cuteness that you can see here? Like this, if name equals main cuteness here, or this unpacking cuteness. Is that something you'd steer them away from, or you just say, look, you know, it works, just move on with your life. I don't care that much.
I might steer them away from some of the extreme compression, like the try except one-liners, just because I think that hides some of the structure of the code. But I assume this also was written to fit on a screen.
Fair enough, fair enough. What would you tell them to motivate them to write their code in a particular style? Because we know that sometimes the finer points of formatting are lost on our scientific users.
I think being able to skim the code and see where you're handling exceptions is extremely useful if things are or are not failing the way you expect. And so them being hidden in one line like this, it's easy to, if this were part of a bigger program, you could miss that you're handling errors in here. Whereas by splitting it out so you see the extra level of indentation, there's a clear visual indication there's something related to error handling going on there, and that you should look there if your exceptions aren't coming out.
Can you make it even more direct for them? Would you tell your scientists, look, if you run some auto formatter on the code, then when you ask me to help you with your code, I'll be able to get back to you faster. Immediate consequence for the action that you want them to take?
I would not hesitate to suggest scientists make use of an auto formatter like Black, just so that they don't have to ever think about spacing, quote types, and any of those things, or line wrapping. It just takes care of it for them. And they can focus on getting their work done, which is what they should be focused on.
I guess I might still ask them to put a doc string at the beginning of the function, because if I just get this function and I don't see the example input and output, I would already have a hard time to just quickly grasp it just from looking at it. So if they just have like a short description of what this function does, it's going to be helpful for me, but that's also going to be helpful for all the other people who might look at it. And then we can see how motivated they are to do this, maybe go a bit deeper and think about what are, do we really need the full power of Pandas here, or can this be done in a more simple way?
Jan,
Yeah.
should they have even bothered with Pandas in the first place? There's a lot of stuff here that looks very anti-Pandas, like iterating through each row of the data frame, absurd drop NAs all over the place, this concat. Could it be the case that they read somewhere on Stack Overflow CSV files, import read CSV from Pandas, and totally missed that the Python standard library has a CSV module? In fact, Jan, I have a question for you. Is this really CSV data in the first place?
No.
Why not?
I guess because you changed the separator and you don't have the same number of columns per row.
Oh, very interesting. So CSV is more than just commas separating values. It's that idea of data with a fixed number of columns. And I think what we can see here is because this scientific user decided that they wanted to use Pandas because somebody told them to use Pandas, they completely ignored that just because the data had a CSV extension, maybe it wasn't really CSV data. Maybe they should have just used the Python standard library CSV.reader. Very nice. Other comments that you would have to guide them to improving the code? And I think, Jan, if you were to give them that guidance, they might have to do more work themselves, but in fact, the code would end up being much shorter. I know I wrote it both ways. And I have a version that's much shorter and simpler without Pandas. Go ahead, Jim.
Well, one thing that was bothering me is the dict comprehension for counts. For k comma v in something that isn't a dict at all. In fact, it's an iterable that is only one. It's a list of length 1. You know, the square brackets xsplit. So it's a list of length 1 with 2 things in it because you just split around an equal sign. And then you're doing qualitatively different things to the left and right, the k and the v. So you know what? I just noticed just talking through this that there's 2 fors. There's 2 for loops in this one comprehension, which is sometimes justified if you want to, you want a nice one-liner in order to flatten some list. But yeah, this is all very scrambled.
Jim, could you imagine that a scientist might have written some code and then they saw that it didn't quite work, so they took it a little bit further and a little bit further and a little bit further, right, and they never really took that step back and said, let me just do this right from the beginning? How do you motivate them to maybe delete what they've written and start over from scratch?
Well, strong motivation would be to show them the much, much simpler version of it. It could have been this, you know. But I also can see how this would happen, you know, especially if, you know, like natural selection and like evolution can be at work on a code base if, you know, the blind watchmaker is making little code edits until finally the result is right.
Very good. And it's definitely a hard habit to break, stepping away and kind of rewriting some of the code from scratch. Now, I noticed we haven't heard from Daniel Margala, Ross Barnowski, Pablo, or Matthew Carbone. Any comments on this code, improvements that you might encourage the user to make? maybe you could see the use of parts of the standard library that the scientists might not be aware of, like default dictionary in the collections module or counter in the collections module. How might you encourage them to make better use of the Python standard library and things which already exist that they're reinventing from scratch?
If you allow me to make some comments here, I think one of the great ways to encourage scientists to actually use that. For instance, I think you're referring to the fact that at the end there is all these counts in the devices, and it's kind of like doing this try except with the only the only reason there is this try except is because the first time you find one of these things in the dictionary is not there, so you need to initialize it to something. There is many different ways to make that try except not needed, like you mentioned, the fold or counter. But I think that becomes it obscures the interesting part here, which is that this code is doing very typical things to do when you're reading a file. You first read the file, then you try to massage the structure of the file into something that you know how to deal with, and then you accumulate some data into something. And these different operations are actually very well defined. The tools that you will use for them are very well defined within the standard library, and sometimes you need pandas, right? In this case, I don't think you really need that. Maybe, if the CSV is ginormous, maybe you will reach for it, but it doesn't seem like the case. So something that I always encourage to, even if it's not like immediately, use the fold or use counter, is to just split this thing into different functions that just does this thing, right? Like parse file, change data into the thing, and then return result, and immediately you will start seeing things that are common. For instance, you will see, why I need to print this thing, like this function that accumulates, so it's going to give me the result. It's not going to print it, it's going to give it to someone else, right? And the same thing for the pandas stuff at the beginning. Like maybe I'm using pandas to read the CSV, but maybe there is other ways, right? Maybe you can switch to something else in the future, like Parquet, right? And what you will find doing these little steps, or what I find with the people I work with, is that immediately they start remembering the tools, right? They know, they will recognize the pattern. I'm just aggregating all these results into buckets. I know that a counter may fit, or sometimes a default date. And here, for instance, the counter may be a bit more difficult to read because, depending on how the data is presented, you may need to do a weird comprehension inside the counter. And the default date is kind of straightforward. It's not much bigger. So, but you see, when you split this function into different ones, you will see all these different decisions instead of a big blob of tasks, right? Like, well, I'm doing all these things. So I would say that the best advice that I will give is like break this thing down, and when you start seeing patterns, then you will start learning about the tools. Because the other way, like if I point out, maybe you could use a default dict, then the scientist is going to learn, maybe in this particular block of the code I will use a default dict. But like the key here is like first the task, then the tool for the task, and that is the way it will stick. That's how I will approach it.
Pablo, I think that's fantastic, and thank you for that. I'm surprised nobody said, hold on a second, scientists, don't write just one giant function that does everything. Write smaller pieces. Does anybody want to comment on this habit that we might have to write that one mega function that does everything at once, and to resist maybe thinking a little bit more incrementally? I think it happens a lot with object orientation as well.
Yeah, I see this a lot. And it goes back to the sort of push-pull in science of, do I write code quickly to get my results, and in doing so kind of mortgage my future, right? Like I basically tell my future self, like, too bad, deal with it. You're going to have to figure out what this does again, in 2 weeks. Or do I take the time now, delay the science a little bit, and write the clean code, write the modular code? It's funny. I can't think of a good reason to write code in huge blocks anymore. I broke that habit in grad school, and it only flares up when I have an especially complicated numerical thing I'm doing, right? Like I can't beat a for loop, so I have to use a for loop and do something, right? And it's a long thing. But I mean, yeah, the modularizing your code is super important. It's going to make it your future self will thank you. Right, if you write little functions and you document each little function, even if it takes longer. Yeah, that's my 2 cents, I guess.
Fantastic. Now, do we have any final comments from Ross or from Daniel Margala before we move on?
There's a question from the audience.
Oh, let's take a look.
In the chat.
And there was a question on whether or not we want to store some information that we're not doing anything with. There's one thing that I'm kind of curious about. Here, when they compute the total values, oftentimes when we write some reporting code, it's really easy to compute a value up front. Maybe what they should be doing is maybe setting this up so that that final projection is just one line of code, but they preserve information all the way down. And to answer the question that came up in the chat, how are we so sure that we won't need the device later on? I think this is a big question that comes up in any sort of reporting code. It's very easy to write the report just to what you happen to need right then and there, to compute very eagerly exactly the summary statistics you have. I worked on a data system once where there was a lot of data being collected, and the people in charge of collecting that data said, well, there's so much data being collected, we'll just sample, or we'll just take averages every 15 minutes. And then a couple of months later, somebody asked for P99 and P95 values, and you cannot reconstruct P95 and P99 from average data. They threw away all the information, not anticipating that somebody might eventually need it. So perhaps what they're doing here in storing that device information is assuming that maybe they may later need it. Does anybody have any comments on guidance for when do you know when you need to collect some data or preserve some information in case you need it later, versus when, you know what, just kind of throw it away and move on with your life. Don't waste the storage. Don't waste the disk space.
Yeah, I know I just spoke, but I can definitely comment on this. And I'm going to focus on like the small to medium scale science, because I think Dan and Tom can definitely comment on the larger scale science because it's different. But for me, if I'm talking on the order of, 10 gigabytes versus 20 gigabytes, right? I want to store everything that I can, right? Because I have so many times, done stuff like this, and data that I thought I wouldn't need, like a reviewer during a paper review is like, hey, Matt, did you try this or whatever? And of course, the answer is no, and I forgot to store that data because I did something like this, and now I don't have it. I have to rerun everything again. So like my rule of thumb, if you're in, doing what I'll call like up to medium-sized science, like you're on the order of gigabytes, right? Is just store what store everything you can within reason, right? Because you never know if you're going to need it later. When you're more than larger science, larger scale science, it gets more complicated, I think. But yeah.
Any comments from our panelists on cases where perhaps Matthew's advice does or does not fit into the scale of science that's being done? Whether you agree or disagree?
Well, sometimes you can't, sometimes you wouldn't be able to anticipate. There's this you ain't gonna need it principle, this Yagni principle. If there's like infinitely many things one could store, you can't. You can't store them all. Like with this example of needing the 10th and 90th percentiles, if you're storing data to be able to compute that, the memory could be very large. Like if you are storing, if you start a histogram with 10 bins, you'll be able to do the median and the 10th and the 90th percentile. But then somebody wants the 1 percentile and then 99th percentile. You would have needed a histogram with 100 bins to do that. And you couldn't have, like, if you didn't know from the start that you were going to need percentiles, you can't guess which percentiles.
Mm-hmm.
So
what guidance do you give when the data is too big to just store everything, as Matthew suggests at his scales, but you anticipate that you're going to need more than what you might be currently storing? How do you find that nice sweet spot? Or do you just suffer and then just suffer the mistakes that you make?
I will go with that. Yeah, because, especially if you're talking about like medians and percentiles, that is not a storage neutral way to collect intermediate values to get that information.
Fantastic. Any final comments before we wrap up our coding exercise? If not, why don't I unshare my screen and I will hand it back over to our guest panelists for today's session, Pablo, who has a couple of prepared remarks that he'd like to be sharing with us. Following the prepared remarks, we will, of course, open it up for Q&A. But while Pablo is presenting, please do feel free to make use of that discussion, that chat widget, and that Q&A widget. We will have our panelists watching that as the presentation goes on to answer questions as they come up live. Now, Pablo, whenever you're ready, if you'd like to share your screen.
Totally, 1 second. Okay, let's confirm. Can you all see my screen? Okay,
I think
fantastic.
we're ready to go.
There you go. Okay, so what I'm going to talk here is a very kind of a bird's eye view of the work that we are doing in the core team to make Python faster, and I will make some comments along the way on why you should actually care about this. Just some small remarks. It's quite generic because there is a lot of technical work here, and I don't want this talk to be very dense. But I'm super happy to discuss any specifics that you are interested on later. Then I will cover some of the most interesting things that we are doing, but obviously I'm going to miss a lot of the groundwork and like details, and I'm sure you will be excited about some of them. So again, I will be very happy to discuss them later if you want, and maybe even by email later. Cool. I'm Pablo. I'm a core developer, Steam Council. I'm also a release manager of 3.10 and 3.11. This is a tiny mistake, but so I can also talk about that later. But let's go into Faster CPython. Okay, so why Faster CPython, right? Like the key here is that, with the many different uses of the language, why are we making Python faster right now, right? In the sense that why not before? Well, one of the interesting things that happened is that making the language, faster is actually quite hard when you're dealing with a 30-year-old language, which is quite weird, right? Like when Python was release, we were distributing the language in floppy disks. So that gives you some remark. Like Ruby was not even there, and many other languages that even sound old today were not even there at the time. So the kind of optimizations that you will do with a language this old are not the same optimization that you will do when you are creating a new language, let's say like Rust, right? So this makes the whole thing a bit harder because, like, if you go for enrich to research, you will not find like how to make a 30-year-old language faster. You will find the shiny things that you could do when you have absolute freedom. So this is the main reason it's taking us so long. So why you should care? Well, no, maybe scientific applications are leveraging code that is native. And we will talk about this thing very briefly, but there is a lot of tooling that you for sure will use that is using pure Python. And by Adam's law, like at the moment you have any specific big, slowdown just by the use of the language, you cannot optimize that by using other, compile tooling behind that. So you really care because you don't want the language to be in the way when you have optimized absolutely everything about your science. So let's go into the details. So one important thing, first let's start with the kind of the big number, right? Like Python 3.11, which is the first time we could reap the the benefits of this optimization. So Python 3.11 is up to 60% faster, which doesn't sound like a lot, but it's really like a lot. Like in previous versions, the improvement between one version to the other was more like 5%, 6%. Sometimes even 10, but right now we are looking at a whopping 60%, which is quite well up to, right, depending on what you're doing. Of course, like this is just Python, as you may know, and you are very well aware. There is things specifically also in the scientific community that is not Python. So you have things in C, C#, C++, or even Rust, right? But these are not going to get faster because we are only focusing on the Python language itself, like the Python code that runs, not code that runs on NumPy or TensorFlow or any of the libraries that you use. So you are not going to see immediately 60% faster on all your applications by running them in 3.11. What you're going to see is up to 60% faster, again, by Adam's law in the Python code. So only the Python code, this is what we're talking about, right? So just bear that in mind. If you just move to 3.11 and you are not seeing 60% on your, numeric code or your Rungecuta execution. Awesome. So let's go into details on how we are achieving this and what are the key ideas of some of these optimizations. In Python 3.11, we made a huge amount of changes. Like we make a lot of changes in the interpreter. Here is some of the ones that we made here, but I'm going to focus only on a bunch of them that I think are very interesting or more interesting to discuss here. The first one is frozen modules. So this is an idea on how to make Python start faster. Why you care that? Because if you make a command line application made in Python, Obviously, if it's going to start some big application that is going to run for a long time, you don't really matter that the application starts very fast. But if you make the tiny tools made in Python to, maybe read a file and change the format or something like that, you start caring about this, because it doesn't really offer a great user experience if it takes this half a second to start, right? So that's not good. So normally when you start a Python, program, what the interpreter needs to do for sure is to, evaluate the file. For that, it's going to load the PYC file if it's there. This is the cache file that is hanging around in your PyCache directories. Then it's going to marshal this file. This means that it's going to read the individual bytes and it's going to make sense, okay, this is a code object, this is a string, this is a number. And then once that's there, it needs to start to heap allocate all these things, right? When it figures out that, oh, I have a code object here, I have an integer, I have a float, it needs to ask the system for memory to hold the thing, because at that time it's just on the file, right? So it needs to say, okay, I need to load this thing on the RAM. And every of these operations needs to be done for every of the standard library files that are used when the interpreter starts, which it's a lot of them, right? The interpreter needs the standard library itself to start, right? Or at least some of them. So what we did is that we say, okay, well, what if we can just get rid of that? And the idea is that we just have that thing done, and when the interpreter starts, has that ready. So conceptually, what happens is that you have the Python interpreter on the left. That's what the symbol is going to represent, and then you have all these files that are hanging around. And reading those files is quite expensive. Grabbing them from the file system is something that you don't want to do. So what we did is basically grabbing those files and getting them inside the binary. So it's basically available inside, and this is achieved by a technique called Frozen modules. And basically, what it does is that instead of storing the code as bytecode, which is what is inside these PYC files, and what Python is able to execute, we transform that bytecode into native C code, into data, basically. So and that data is statically compiled into the interpreter. Maybe this sounds a bit complicated, but the idea is that at the very end, the interpreter has inside already this part of the standard library ready to use. Not everything, just part. And some of the standard library still needs to be read by reading files, but sometimes it's just inside. You can actually check this using certain programs, for instance, in Linux. What you're seeing here is all the system calls every time the interpreter goes to the operating system to ask for some resource or something that needs to be done. And as you can see, you can see that the time every operation takes cumulatively and how many calls. Like the first one, this with a funny name, new fstatat. This is basically reading a file and checking if it's there, among other things. Right? It checks the time, something like that. And as you can see in 3.10, which is this one on the left, that takes a lot of seconds. If you say do the same experiment in 3.11, you will see not only that the number of calls has been reduced, but the number of time that call takes is quite lower, right? Which is, lower is better here. So that's one advantage. Now the interpreter actually starts much faster. You can see it in the last column. 3.10 is 0.1 and 3.11 is 0.07. Again, not like super game changer, but like we are trying to slowly getting it faster and faster so it feels snappier. So there's more optimization to make Python start faster. Okay, so what about running faster? So the first thing I'm going to talk is about doing cheaper frames. So what is a frame? A frame is basically all the information that the interpreter needs to know how to execute your function. Things like local variables, or like every time you change the variable content, where I put the content of the variable, or how much memory does it take to execute your function, things like that, right? Like if you're used to coding C and C++, you will know what a frame is. In Python, there is a kind of a problem here, and the reason is because this is not very well laid out in memory. So, for instance, in 3.10, this funny icon is going to represent one of these frames, and the bar is the memory in your computer. So, what's going to happen as you call more function is that Python is going to say, oh, I need a new frame, and it's going to literally call memory from the system, and it's going to allocate the frame really far away in memory. And when some extra frame is needed, then it's going to allocate it in some other random place. And, they form a linked list. And when a new frame is needed, it's going to be there. And this is fun. This is really bad because if you are aware of how memory more or less works, when you have something that is very close together and you access it from left to right, that is going to be very, very fast. And this is neither close together and it's not read sequentially. So that's quite bad. And this makes calling functions and uncalling functions, like basically return from functions, very slow. So something that we did, which sounds very simple to do, but actually is very complicated, is to don't do this layout and don't do this allocation of memory. What we do is that when you call a function, we just pre-allocate a big chunk of memory, and then every time you call a function, we just use some space that is following that. So it's just close by, and then you call another function, and it's just there, and another function, the same idea, and another function. And when you finish calling a function, we just remove that from there, which doesn't really mean removing the memory. It just means moving a pointer back, because we just are done with that. This means that we don't need to allocate more memory, and also it means that when you are calling and returning from functions, you have this cache, cache friendliness that you normally need. And this actually makes a huge amount of difference. In particular, it makes like up to 20% depending on the number of calls. Like for instance, if you call a lot of functions or a lot of methods, you're going to benefit a lot from this example, because you don't need to do all these allocations. Something else that we have done is that we have figured out that a frame has a lot of information. So for instance, this is kind of like the frame content. So something that a frame has apart from the information is this linkage information, like what is the next frame, which is the previous frame. This funny back is basically debugging information, like what is the line number associated with the instruction. This is important because when your instruction fails, like you divide by 0, you want to know the line of code that was associated with that. And then you have other things like metadata that is used by the interpreter, but it's not always used there. And so we realize that we don't always need all of these things, right? So, and the less things we really need all the time, the faster we can allocate things, because the smaller it is. So what we have done is that we have break basically these frames into two chunks. The real information that you need, like locals and like things that you store, and the linkage information, like what is the next frame and what is the previous frame. And then we have put the rest of the information kind of like on the side. And this information is only created or linked to the frame when you actually need it, like when you really need for instance, you're creating a generator or in some other specific information. We create this what we call, it's a bit confusing the names, because we have 3 different names for the same thing, but this is called a Python frame, the actual Python object that you can look. And this is only created when you ask for it. So for instance, the interpreter sometimes says, oh, I need to see a Python object for a frame because an exception is raised, or because the user called a function called sys.getFrame that returns you this frame. So at that point, we just create this Python object that has all this information as you expect, and then you can interact with it, but only at that particular time. Obviously, if you do this thing, it will be as slow as previous versions, but if you don't, then it will be much faster, which is great, right? This makes the whole thing, makes this thing up to 7% faster in total. One of the decisions I'm very, very excited about is this idea of inline frames, and this is something that I work a lot in first year. So the idea here is that, for instance, if you look at a function like sum, it's going to add 2 numbers, and then you check, okay, Python, tell me the instructions that you are going to execute when this function runs. As you can see, it's very simple. It's going to make 2 load fast. This load fast basically means like load the variable x into memory. The value is 3 or 4, so it's going to load that thing into the stack. Then it executes a function called binary add that is going to do the addition itself, and then return value is going to return. So very simple for instructions. If you look here, there is a specific important thing, which is that who evaluates this function, right? Like what part of code evaluates these functions? So in CPython, that is called PyEval frame default. It's not really important. It's just a very ugly name. So we are going to call this thing evaluation loop. The evaluation loop is basically going through every of these instructions and is going to execute them one after the other. So what happens when you call 3 functions? Well, if you check the C stack, like the actual native code that runs every time you call a function, you're going to see that every of these Python functions corresponds to 1, 2, 3, 4, 5, 7, 6, 7 C functions. So basically, those are 7 functions. This other function is another 7 functions in C, and this last call in Python it basically corresponds to 7 functions in C. These functions are doing things like passing around parameters. They are not actually doing anything useful. It's just like the structure of the interpreter. They execute really fast, and they don't really do a lot of things, but they are important. Why they are important? Well, if you look even more closely than this view, you look at the assembly code, you're going to see that independently of what the function does, again, don't really look into this function. It's not important what is happening here. This is ARM AR64 for the evaluation frames, but you're going to see that always, every time you call a function, at the beginning, at the bottom, there is always a fixed number of instructions. In this case, it's the first 2 and the last one. And here, you need to pay for those. Even if your function doesn't do anything, you need to pay for them. So if calling a Python function basically means calling 7 C functions, you're going to pay 7 times for this small amount of time. And this is really, really bad, because it makes the interpreter slower for no reason. So the idea here is that, instead of doing this thing, what we can say is like, okay, so why instead of like, calling all these Python functions just to create a new evaluation loop every time you call a Python function, why don't we reuse the same one? And this is possible because at the end of the day, the idea that we want to have is that we have this evaluation loop, and this evaluation loop has like a frame and it has a call object because it needs to know what it's going to execute. And if you call another function before, we just need another one of these that has another frame and another call object. So, and every time you create one of these evaluation loops, you need to pay for all these overhead, 7 C functions. It's a lot of extra overhead. So the idea is quite simple. Instead of doing this structure, we do this other structure when we have one only of these guys. And then this thing has the call object that needs to get executed. And then we associate every call object a frame because that frame is executing the code. If you make another function call, instead of creating one of these evaluation loops, what we do is link the call object to the previous one. And that new call object will have another frame. But we reuse the same code. That's what is called inlining, because instead of actually calling something, what we are going to do is basically swap the data, and with enough information to go back when the function returns. Basically, the linked list here, and we don't need to call another C function. We just swap the data inside, and this basically allows us to skip these 7 C functions every time you call Python code. This actually means that in theory, if you only code Python code, there is no recursion limit anymore. You can make the recursion limit as big as you want, as long as you don't call NumPy or things like that, or parts of the standard library that are making C. This can make Python 170% faster, specifically when you only call functions, which obviously is not realistic code. But for instance, you do a Fibonacci function or like a recursive factorial function, you're going to see some brutal overhead just because most of the time is just calling things. Obviously, you're not going to see this, but the important thing is that in some scenarios, this can be actually quite costly. The last thing that I want to discuss very quickly as well is something that we are very excited about, and we are even making better in Python 3.12, which is called Quickening. So what is Quickening? The idea here is that, let's go back to this function, for instance, just add numbers. Again, we have seen this code here. But if you look closely, you will see that this binary op, like this is how it's called in Python 3.11 and 3.10, I think. This binary op is quite generic. It doesn't know what X and Y is. Like, it can be anything. It can be strings, and when you add the strings, they concatenate them together. It could be numbers, and if you add integers, then it does something different. If you add floats, it could be an integer and a float. And this thing needs to figure out all of that. Like, binary op needs to do all this crazy work about like, oh, what are you? Oh, you are an integer. Okay, let me just do the thing for integers. And that, every time you call it, is really, really costly. So quickening, basically the idea is that when you call this function a lot of time, like around 1,000 times, with the same data, the interpreter is going to figure out that you are calling this function with the same data, for instance, 2 integers, right, or 2 floats, or 2 strings. And then it's going to change the code on the fly, and it's going to adapt to it. For instance, if you call this function a lot with like integers, first it's going to basically, with floats in these examples, or 100 times, then it's going to change to this other version that we are seeing here. First, it has made something that we call a super instruction, because all this code starts with 2 loads, like for X and Y. And here what it does is that instead of doing like one load and then the other load, it's doing 2 loads at the same time. The reason there is a third load is because we cannot change the number of instructions, but this second instruction, that is the single load fast, never gets executed. So the first instruction does everything and jumps 1. And then you are seeing that there is this binary op adaptive. So this thing has learned that you're passing floats. And that thing is going to, well, in this case, is particularly at this time is still learning. If you keep calling with floats, the binary op is going to be called binary op floats, add float. But in this, as you can see, the instruction itself has changed. And if you keep calling and calling and calling, it's going to change to, it's going to change to another thing that just knows how to add floats. And that is going to be extremely faster than just the generic version. And this is really, really good. If you start passing some other data, then it's going to figure out that you are not calling it with floats anymore. So it's going to go back to the adaptive version. It's going to try to learn again. If you're keeping passing different data, it's going to, stop trying to learn, because learning is a bit slower than just doing the whole work again and again. But if you keep calling functions with the same patterns, which is something that you probably are doing constantly, then it's going to be much, much faster. And this is really, really important. There is a lot of different instructions that the interpreter has, so we have implemented only a bunch of them. Particularly in 3.11, we have implemented all of this. So things like, access subscripting list and calling things, and like accessing attributes, loading globals, binary operations. But in 3.12, we plan to add even more than just this. This is the let's call it easy ones. They were not easy. But the idea is that, with all of these things, every time you do one of these things, the interpreter is going to learn that you're calling it with the same things, and it's going to make it faster. In particular, how fast? Well, this can be 20% faster, just because it's a very typical thing that you're calling the same function with the same kind of data. Not the same data itself, like 3 and 4, but the same kind of data, like integers or floats. And you're not changing the same function to just suddenly, call it with the strings or something like that. James, how are we on time? Maybe we are very close to the end. Depending on how we are, I can talk about an extra one or just leave it here and start the discussion.
Feel free to take as much additional time as you need. I think this is a fantastic discussion, or fantastic remarks.
So the last one I would like to mention, we call it faster dictionaries. And as you can see, some of the things, and the reason I choose these particular optimizations were because we are trying to attack different topics. The first one, as you saw, is about making interpreters start faster, because that benefits a specific set of users, like command line tools, for instance. Then I talk about like how we make the runtime faster, like when you're running Python, how we make it faster. So there's this idea of faster frames and things like that. And how we can leverage repeated patterns in the interpreter, because that is something that happens a lot. So what I'm going to show you is another way that we are attacking this problem, which is how to make faster like certain accesses, but also how to make objects smaller, because that is important, right? Like, not only making things faster matters, but also not bloating your memory with just all this extra metadata that we need, all right? And that is quite important for us. So we are also trying to tackle that problem. And this optimization that I'm going to talk, we call it lazy dictionaries, and it's a bit of a mix. It does both things. It makes it a bit faster, and it also makes objects a bit smaller. So let me go into detail. So imagine you're doing just this, right? Like you have this code, have an instance, and then you access an attribute on the instance. As you know, Python is extremely dynamic, and this, simple operation really can be very, very complicated. Sometimes you can look at these crazy diagrams that you can see online that, will tell you everything that happens depending on the structure, like you have meta classes and things like that. It really doesn't matter. You don't need to know any of this, but it's just that simple line is very, very complicated. But it's also quite common. It's very, very common to access attributes on instances. Is the core of object-oriented programming, maybe with the exception of calling things on the instance, but it happens all the time, and it needs to do a lot of work to go into there. But even if you ignore this, just even if you don't care about this thing, and you just zoom into the easiest case ever, which is just I have an instance, the instance has inside a hash table, and I just want to get the thing from the hash table. So you just forget every of this complexity and just look, okay, what do I need to do in the simple case? So let's look at what you need to do. So let's start with the object. An object is basically an address in memory. It tells you where the data for the object is. And it's very simple. It's basically the type of the object and the reference count, right? So let's say we want to access an attribute on this object. So how CPython does it currently? From the object, it needs to go to the type. It needs to say, okay, are you an integer? So, okay, let's go to the integer type. Why? Because the object itself turns out that it doesn't know where the dictionary of the object is. That's like there is historical reasons, but that's what happens. The one that knows where the dictionary is the type. So the type has a particular field inside that you also need to access. So there is 2 pointer the reference already that will tell you how far from the beginning of the offset is the dictionary. So once you know that number, you go to the offset to the object again. You move your pointer that many bytes, and then you find the dictionary. Fantastic. That's another object. In this particular is the object dictionary, right? But that thing is a given offset from the original that you started with. But you're not done because you have the dictionary, but you want the actual value. So you need to go and access the keys of the dictionary because you want a particular attribute, let's say foo. So you need to go to the hash table and find the key foo and doing the hashing and all that stuff. And once you have that, you need to reference yet another pointer to get the value. So if you start counting arrows, there is a lot of arrows just to get one single attribute in the easiest case possible. All these following arrows takes time. Why? Because every time you access a pointer that is very far away from the start, you need to throw all the cache out. And you do this again and again and again, you cannot benefit from the cache that is very efficient inside the CPUs, right? And this is really bad. Not only that, but also it takes time because you need to read another memory location and then another memory location and then another memory location. And that is bad. So what we have said is that, okay, we already know that most objects like of the same type, normally they have the same attributes. We already know that. It's quite common, right? You have a class house. House has door and window. Normally, all instances of the class house will have door and windows. Python allows you to do more than that, but normally, most of the time, most of the objects of the same class will have the same things. And we know that from a long time ago. But we can now use this knowledge to go a bit further and improve all these arrows. So the way we do that is that instead of having that thing there, we are going to do the following. So the type of the object now is going to have the common keys. So in the case of the class house, it's going to know that most of the time houses have doors and windows, and we store door window in the object. So when we want to access the value, instead of doing all this where is the dictionary and blah blah blah, well, it turns out that we don't really need a dictionary. Like, why would we need a dictionary? We don't really need the whole full Python dictionary with a hash table inside. All that thing is not necessary. We just need the keys and the values. And first thing, most keys are mostly the same. So let's just store them in the type. And this is more or less how it's laid out in memory right now, but we can now even leverage it more because we don't need to really go to the dictionary. So when you just have the simple case, all the objects have the same keys, and you access one attribute now, it's going to just do one jump to the type. From the type, it's going to go to the keys. If you're asking for one of the keys that is there, like let's say door, then it's going to tell you, instead of like, oh, where is the dictionary? Let's go to the dictionary access. Instead of all that thing, which is very complicated, it's going to tell you an offset in the object where the value is. So now, instead of having a dictionary and the dictionary has keys and values, we are removing the dictionary and we are storing the values on the object itself and a fixed offset. And the keys are in the type. There is a bit of complication here that I'm obviously not showing, but the idea here is that we don't need the actual dictionary object. That is the whole key of this idea. The dictionary object is just for convenience. But it's not really needed. So we don't need to know that it's an object in Python. We don't need to know that it's a dictionary. We just need the keys and the values. But you may say, okay, but like this is a simple case. What if I do I access __ dic __? That needs to give me a dictionary. When you do that, then we say, okay, now you're asking for a dictionary. We need to create it, and we will create it for you, and we will change all these arrows to a more efficient shape. But now you have the dictionary. So the dictionary will work the same, and you can access the dictionary. An interesting insight here is that if you ask for the dictionary, we need to create it, so the object is going to get a bit bigger. So if normally you try to access the size of an object by doing like size of the struct plus size of the dictionary, you are implicitly creating the dictionary, so it's going to be bigger than the real answer. That's a small, tip. But as you can see here, only if you ask for it, then we create it. Now the access is a bit more inefficient, but it still works. So existing code will not know that we are doing all these things. And it will keep working. But if you're doing efficient access, which you are doing anyway most of the time, then it will be better. Obviously, you can say, well, but this is great if you are always using windows and doors as the keys. But what if I now have a specific house that has now a coffee machine or something? Then we will create also a new set of keys, and we just switch the arrow from the dictionary to this new set of keys that is exclusive to that particular object, and the access will be even more inefficient, because now we need to figure out that there is two set of keys and things like that. But the thing is that even if you do that, it will keep working normally. The important thing here to know is that if you compare the number of arrows in the best case and before, we have less arrows, we have less objects, and therefore we have faster access times and less memory. In particular, this can give you even to 30% smaller objects if you really do like efficient access patterns, and the actual memory offset from the from the actual objects are good enough, which I can explain later what good enough is. But in the best cases, you can get up to 35% as we measure. Well, and these are like three of the ones that I'm more excited about. Of course, there is many more details here that I'm missing, and many more optimizations that we have worked hard about it. But we keep track of how things are going, and obviously it's not just from one day to the other. So we have this web page, which really looks like a C programmer learned HTML yesterday. So I acknowledge that the web page is not the most exciting one, but it's speed.python.org, and in that we run a bunch of benchmarks. So we have this idea of a macro benchmarks, which is obviously not like as big as a scientific application, but there is things like embody simulations, and like different kind of algorithms like ray tracing, recharge, time marks, things like that. And all of we keep track of how fast all these macro benchmarks are over time, and we know the effect of the things we do, and we are keeping an eye on this all the time. So not only we know how fast Python is getting from one version to the other, but also we know how if some of the optimizations we made actually made some go faster but not some other. So, and this is public. This is something that you can see. Release managers look at these numbers, and obviously some of these benchmarks will be faster. Then, as you can see here, this is from one of the snapshots. I think this is in one of the last betas. Some of the benchmarks are actually even twice as fast. For instance, Delta Blue, which is in the left image, got 1.96 times faster, which is almost twice as fast. Some others are a bit like 10% faster, like depending, right? And maybe I think that the last one is 6% faster or something like that. So your mileage may vary, but most of the time we see a lot of speed ups. Sometimes we see no speed up whatsoever because you're using a lot of compiled code. You will have some like just calling functions. Your code is going to call functions, and nevertheless, but maybe it's like a small percentage of your runtime. And again, the third time I mentioned Andon's law, you will not see all that tasty 60%, but hopefully you will see it in 3.12, right? Because we are keeping working on this. We are still learning how people use Python most of the time. Even if it's a very dynamic language, it turns out that people use that dynamism only in specific cases. Sometimes it's not really important. Like for instance, running test suites is one of the most dynamic uses of the language, but it's not that mission critical to have test suites run extremely fast when we can make sure that your scientific applications or your tooling or your job schedulers or your data pipelines runs faster, right? So we are still learning, we are still in contact with people, and people are even suggesting more and more of these benchmarks that we can keep track of it. For instance, we didn't have any async.io benchmark for Python 3.11, but we have now like 4 or 5. So if you're interested in this, one fantastic thing that you can do to help us make sure that your case is covered is to propose one of these benchmarks. And there are some rules, and you can learn them from the repo. But like if you are really into it and you want to help, this is a fantastic way that you can say, like trying to encapsulate in a very simple example that doesn't take more than a couple of seconds your particular use case, and then give it to us to try to analyze it. Sometimes we add it to the suite if it makes sense. Sometimes we tell you why we cannot, but proposing it is already good enough. And that's basically it. I think I have overrun a bit of time, so apologies for that, but I hope that I can answer all your questions in the Q&A section. We'll stop sharing right now.
Fantastic. That was amazing. I know I have a bunch of questions, but I want to open it up for our host panelists or our audience to ask some of their questions first.
Could you say again the address of the benchmarks? There was something on the python.org domain.
Yeah, I will paste
I'll put it in the chat as well, speed.python.org.
Thank you.
Yeah, again, the webpage really looks like quite outdated, but remember that we are language programmers, not web developers.
Yeah, those in the know should take it more seriously as a result.
Right. Yeah. When there's not a lot of CSS, it's serious.
There was a question from our participants. Matt asked, does or can binop adaptive be taught to deal with non-built-in types, such as NumPy and D arrays? Is it as simple as an object with an add method included in the adaptability, or is there some registration, or does this have to be built into your PyEval frame loop?
Right. So an excellent question. At the time, this is something that the interpreter needs to know about. The reason is because at the time we build the interpreter, the actual C code that needs to run underneath needs to be available. NumPy and Pandas and other things will be loaded at runtime via DLOpen normally. And this means that code is not known when the interpreter starts. So unfortunately, we cannot build into the interpreter all these things. So unfortunately, at the time at least, and I think for a long time probably we won't allow to do extra registration, although we know it's kind of theoretically possible. But at the time we are focusing mainly on built-in types, not only because it's much easier, but because when you offer registration APIs for third-party code, it means that you need to maintain those APIs. And as we are changing the interpreter quite heavily and aggressively, we don't want to, put ourselves into a corner and then having problems precisely changing something as core as that. And this is important for us because, as you probably are aware of, moving to a new version of Python with the scientific stack is not always easy, and sometimes it's even very challenging for everyone, users, us in the core team, library maintainers. And, sometimes it's very tempting to do these fast paths and like reaching to the internals, like Python does, for instance. But sometimes, you have to pay on the other side. Now, your code won't work on 3.12 as easy. So right now we are being very cautious, but it's theoretically possible.
There was another question in two parts. The first part was, are there plans to keep focusing on speedups beyond Python 3.12?
Yes, so I didn't mention this just because of the lack of time. So this is mainly driven by a team at Microsoft called the Faster CPython team that Guido van Rossum, which is the creator of the language, is driving there. But also some collaboration. For instance, I have 50% of my work time to work there, a part of my open source time, and there is more collaboration there. And these people, as of today, are still hired by Microsoft. So there is still, hunger for continuing the project, and we have already plenty of things planned for 3.12. And probably in the future. Well, things, it depends, but yes, certainly 3.12 or even more, as long as everyone is happy with the collaboration, and so far they seem to be. Yep.
The second part of the question was, are there plans for a version of CPython without the global interpreter lock? And I presume they're referring to some of the recent attempts to eliminate the global interpreter lock. Is that?
Well, that we need another entire session to answer. I will do my best here. So the short answer is yes, there is plans for it, in the sense that there is a proposal and that a person called Sam Gross proposed. So he is an excellent technical person. He works at Meta, and he spent a lot of time these past years making a prototype of a version that doesn't have the GIL, and he made a proposal. Regarding your actual question, I suppose if really that will ever happen. Well, it's very difficult to say. It certainly is possible. So right now we are evaluating the proposal. The proposal is very dense. It's the fourth most long PEP or something like that. So it's quite big. It's quite technical, and among other things, it introduces very important changes here. And these changes affect the Python ecosystem, and specifically the computing ecosystem and the scientific ecosystem. Why? Because it sounds very interesting, doing this kind of like removing the GIL so you can run actual threads. But turns out that this forces every one of your dependencies to know that the APIs that you're using are thread safe. And right now, this is a very difficult task, and it's an enormous burden on your library maintainers. It's very difficult to just say, as a library maintainer, like a NumPy maintainer or a TensorFlow maintainer or something like that, my entire Surface API is thread safe. It's very difficult because most of these libraries were built on the assumption that there is something big that protects your thread and safety. And it's very difficult to just locate all the state in your programs, in your library that is, is even in danger. So you can even look for it. And turns out for reasons that automatic tooling doesn't really work. So thread sanitizers and things like that doesn't really work here because like it doesn't know what that API is, right? Like it doesn't know what the API in Python. So again, this doesn't mean that it's impossible and it won't happen. It just means that even if we are very excited about in the core team, we say, yes, let's make it happen. This means that the moment that the thing happens, it's going to put a huge toll on everyone. And it means that, we don't want Python 4 to be the Python 2.3 again, right? So right now, it's being considered. It's certainly possible. It's a possible future. Will it happen? I don't know. It depends. Right now, it's being discussed by the community. So you can be part of the discussion as well. The discussion right now is open. We are not making any final decision. If you are concerned or excited, you can go to the discussion page and comment it. Like you can say, oh, in my particular scientific program, I will really benefit from having real threads because yada, 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 or I'm a library maintainer in Matplotlib and it will make my life hell, please don't do it, or I'm a library maintainer of this other thing and it will be fantastic to do it, I will find a very simple way to make it happen in my library. We really want to know about this because at the end, we don't want to make people suffer for no reason, and we want to know all the problems and all the benefits from everyone, right? So right now, the best thing you can do if you are excited about it or you are afraid of it is to go to the discussion thread and comment it on, because otherwise we cannot know what your concerns or excitement is. So sorry for the kind of complicated answer, but I hope that mostly covers it.
Jim, you have a fantastic question. I'd love to invite you to jump on audio and ask it. I'd add a little bit of framing around it myself, which is historically the CPython interpreter has been something which any motivated postdoc could just kind of read through without a whole lot of knowledge of C code and just understand. And with some of these optimizations, it reaches a level of complexity where that's no longer the case. Jim, would you like to share your question?
Sure, yeah. So the question comes is primarily through Numba, but uncompile 6 is another use case. These are both packages. Numba in particular is, it takes a function, a Python function, looks at the bytecode and replaces it with LLVM in order to run that restricted function. Not everything can be compiled like that. But it can be like hundreds of times faster. So it's a big qualitative distinction.
Mm-hmm.
So it's a fairly large team and quite a lot of momentum behind it. But with each new Python version, you can imagine the bytecode is different, and in particular the bytecode is more subtle and more complex because it's being well optimized. So there's this one need to make regular Python execution faster, and then there's this other more niche but still real need to be able to do things like what Numba does or what uncompile does in order to disassemble it. Hearing about the problems that the Numba team has with each new version, and it can take many months to adapt Numba to a new version of Python, I've been wondering if it might be possible, since this works by a decorator, there's like a at numba.jit, and then there's your function.
Right.
If it might be possible to introduce some sort of mode for decorators, specifically decorators, to say that this particular function that follows the decorator is not optimized bytecode. It's some old version of the bytecode, some simple, stable version that would give developers like Numba and Compile an easier time.
Right. So let me answer. There is many. Thanks a lot for the question. It's super interesting, and I want to actually touch many things that you mentioned. So sorry if so bear with me. I will be a bit of a long answer. The first thing I want to say is that I acknowledge this. This is very important. Myself, my background is actually physics, so I'm very aware. I have used Numba actually in the past. There is a problem here. First, the challenge, not a problem, like a challenge. The challenge is that there is in the Python world in particular, and I think this is more acute in Python than in other languages, that there is all these things like Numba or Python or like very core applications on the Python ecosystem reach from undocumented and internal parts of the interpreter, right? The bytecode is not documented to be stable. This means that we can change it on every version, right? There are other parts that more or less are stable, like AST, and there is still no guarantees. And there is other parts that are very stable, like the APIs that we offer. We already have a huge burden maintaining the APIs that we offer. You can imagine the incredible burden of maintaining the other things. This doesn't mean that we don't care, right? This is very important. For instance, Python comes again and again and again, and it's even like a bigger surface problem, not more important, but it's a bigger surface problem just because it has more users everywhere, and it's a core dependency that, users have this trouble moving to new versions because something that Python used to reach for secretly now doesn't work because it's not there. And we have this conversation with the Python team. So first thing I want to say that we are aware of this problem. But I want to highlight first that it's a very challenging problem because we are already having a challenging problem maintaining and evolving the APIs that we actually say that they are stable. And now when we have to consider all these other cases, it's just an unbound number of them. So for giving you some light to this, it's not only these tools like Numba that you mentioned, but also like profilers. Profilers need to reach into very core and internal parts of the interpreter, things like PySpy or Austin, or I don't know, now there is a lot of them. I myself maintain a memory profiler as well that does the same. And these things break every time you change the version. Sometimes this means that, you just need to change because that's what you buy in when you are a profiler author. But the same way the Numba team buys into the thing. But sometimes it breaks irreparably, and now it doesn't really work because there's no way around it. So in that case, and this is very important, the most important thing is tell us, because right now the NumPy team has an issue open for moving to 3.11, which is, I think, is very popular for users to go there and say when this is going to be fixed and things like that, putting a lot of pressure on the team. On the Python core team, we have not learned about this. I know it because I visit the some of the issue trackers of different repos as a release manager, just because as a release manager, which is one of some of my obligations, I want to know who is going to have a hard time moving, right? And I want to, tell the different people in the team, and I want to be informed. But to discuss in depth these issues, we need some representative or someone from the team to tell and say, hey, look, we are having all these challenges on 3.11, what we can do. And this is just one page of the problem, because, for instance, there is people maintaining JIT compilers, and you can imagine that it's the same thing. And they have other problems, right? They want to have callbacks on call objects and things like that. And the more we give to this group, the less we give to the other group, because JIT compilers don't only want to not have the decorator that you're proposing, but they want to forbid that to even happen, because they will not able to JIT compile the whole thing, because they don't even have they are not operating on the vehicle level, right? And they have their own evaluation loop, so they don't want everyone to own that part of that, right? Because otherwise they will need to uncompile it and de-optimize it. So what I want to say here is that yes, it's important, and we are keeping again an eye on it. And even if sometimes we say, oh, we will technically change all these things, we are not going to, because it will break irreparably these projects. Sometimes we need to say, look, these people are buying into it anyway, because when they started the project. But we always want to make sure that all of our users are heard. And again, I want to emphasize that this is the most important thing. Reach to us. We have right now we operate mostly on the Discord server. Discourse. I always confuse both, but the Python thing is discuss.python.org. Or if you want, we obviously are always on the mailing list as well. But it's very important that the library authors reach to the team. Look, if people find it hard to reach to the mailing list and do it in public, they can also email us. They can email the steering council. There is a email address, steeringcouncil@python.org. If they want to reach the the people that make the final decisions, they can email the release managers if they want. All these emails are public. Or they can open a public discussion as they want. Or they can also reach core developers that they are a bit more in tune with or they know about. So all these possibilities are there. But the most important thing, and I want to repeat it again because, as a steering council and release manager, I find this thing critical, is that at least the first thing is that we need to know about the problems in technical, with a lot of technical detail. Even if the answer is sorry, like this is what it is. But sometimes we say, okay, for instance, let me give you an example of when this happened. Like the people from PyBind 11, which is a very popular library to do binding in C++, come to us and say, look, we are reaching to these horrendous internals to create meta classes and things like that. And I think this affected NumPy at some point. But this is horrendous. It breaks every time we upgrade. This is really bad. Like, give us an API for this. And we think about it. And now in 3.12, there is an API to create meta classes, and they can call the thing instead of doing the ugly thing they were doing. Why? Because it turns out that was kind of a good thing that we could do. It didn't cost us a lot, and it solves a big problem for them. It doesn't really put us in a weird scenario when some people suffer and some people don't. We accepted the toll, and it's fine, and everybody is having a nice time. Sometimes we need to say no. For instance, some provider authors reach in and say, hey, what we can do here, and we say, well, it's complicated. We are still thinking about it, but we say, probably you're going to have a bit of a hard time in the future, but we hear you. We are still thinking about it, and maybe we actually propose a PEP just because we cannot just do it. But as you can see, the common denominator of all these cases is that someone from the project reached to us in some way or form and told us, hey, look, we are really, really struggling for this. Obviously, you cannot do it every time you have a small struggle with a library that does these things, but for some core issues, like if you really take like 6 months to port to 3.11 and you are someone like NumPy or Numba or some big project in the scientific ecosystem, then we are obviously going to, we are going to listen to you even if you are a random developer somewhere doing their tiny library. Everyone matters, but we have a very diverse set of users, and we need to balance all these things. But again, the most important part is reaching, and so we know about the problem in a detailed way, and we have an open line of communication. Sorry for the long answer. But yeah, I can tell you at least from my side and with my foot in the steering council and in the release team that we are aware of this, and in particular these NumPy issues. I am aware of it, is on our mind when we do these things. Maybe I take the critique if some people are not happy with the result, but we have it in our mind still.
Okay, so when I next talk to the NUMBA group, I should point them to discuss.python.org, any particular category within it.
Yeah, core development.
Core development, yeah. And the steering council.
Yeah, if they want to reach to us because for whatever reason they don't prefer a public discussion or they want a different forum, we are always happy to learn about these things on the Steering Council. I think it's a Steering Council at python.org, but if you do a quick Google search, you will find the address. Another option, if you want, is that they can open an issue on this repo. A second. So in this repo, they can open issues. This is it's also reaching to the Steering Council. I'm pasting the answer on the chat. No, so I don't know if you can see it. Yeah, so it's Python/Steering Council. So here is the same. It's communicating with the Steering Council, but in a more public way. So this is the kind of path that people do to propose PEPs, like Python enhancement proposals, but also other things like we are discussing about this and it's impossible to reach an agreement. What should we do? So, but also like, hey, we are the maintainers of blah blah blah, and like we want to reach to the Steering Council because this and this reason. Obviously, a more public discussion is better, but sometimes if you want to directly go to the Steering Council, you can. So I hope this gives you some options.
Great. And I think we have time for one final question before we wrap. I know, Ross, you have a fantastic question. I'd like to invite you to jump on audio and present that question for Pablo. And Ross, you may be muted. One more time. I'll pose Ross's question while he sorts that out. Right. He wanted to know, Pablo, to your knowledge, have there been any conversations among CPython developers regarding the use of static typing information at runtime for further quickening? Now, Ross, do see if you can get yourself on audio if you need to add any additional detail, but I'll leave it at that for Pablo.
And an excellent question as well. The answer is yes. So not only this has been discussed, but also there are certain other implementations of Python or forks of Python, like Cinder, which is the one that Instagram maintains, that actually leverage this. There is a bunch of caveats here. One of the caveats is that for making it really, really fast, they need to implement what they call static Python, which is like a opt-in restricted set of things when you can say, oh, this importing this module won't have side effects and things like that, and understand definition of side effects. So it's not that easy as just, oh, here's some types, so I'm figuring it out. The reason it's not that easy is because there is this idea of, sorry if I'm getting into a lot of technical detail. I can give you a more high level view if you want, but like there is this idea of guarding, and the guarding is basically saying, okay, I promised you from my type system that this thing is going to be an integer, but what happens if it's not? And the reason is that crashing is not an option. Like it's never an option, right? So even if you say it's an integer and we believe you and we put the optimization there or whatever, we always need to check if you really pass an integer or not, right? And sometimes the check is more expensive than not doing the check and doing the generic thing, depending on the operation and the particular function or the type, right? And this guarding needs to be done on every possible path and intersection of the different types. Like what happens if this is an integer and this is a float? What happens if you pass me the thing on the reverse? But it gets quite complicated. And there is all this idea of like guarding machinery. So how this make this guarding efficient? And this is something that JIT compilers need to do, because JIT compilers need to say, can I optimize this function with native code? And what happens when that doesn't happen? I need to undo this and have the generic code. So we share some of these concerns. This is done in Python right now with like, I will call it a bit of primitive guarding, in the sense that we have some guarding, for instance, for has this dictionary change, or if you alter the type, for instance, or has this function code change or things like that, or has this been optimized. But like guarding for every single type and function is complicated, and we don't want to make a kind of naive version that optimizes something but de-optimizes the whole world. So we are investigating what we can do and how generic we can do it. We have some very good work, again, by the Cinder people over, very strict versions of Python that can leverage this a lot. But we are certainly looking into it. One of the efforts actually that we are doing in that direction or general direction is that we are actually changing a bit the Python compiler. the thing that basically compiles your code, and to make it a bit more flexible, to start adding these things around. And we are still very early talks. We're even thinking about exposing the internals of the Python compiler, so we can prototype in Python these changes in the Python compiler. So we can say, well, it's not production ready, but can we iterate a bit over this idea of typing instead of having to write C code? Can we expose these things? Obviously, we don't want to expose very core things of Python because we don't know what happens. We know what happens. Like what happens is that James Powell comes in and does some atrocity. But like it's always a thing to consider. But yes, this is something that we're considering. I just want to communicate that it's very tempting, but it's also very complicated. It sounds very cool in in practice. Sorry, in theory. In practice, it's complicated. But we are exploring some options around, and even preparing a bit the code base for some possibility. And again, some code that you can use, like Cinder, is actually open and is compatible mostly with CPython. Well, I think it's 100% right now. You can actually leverage that speed by using Cinder if you want. So that's another possibility. And of course, there is MyPyC and Python, I think, in some way or form uses that information to create compile code. So you still have options if you really want to leverage those hard, types in your code base to make it faster. Obviously, with drawbacks. And in general, we are looking into it in CPython, but complicated. Doing things on CPython is always more complicated than doing it in third-party projects for many reasons. But yeah. Again, sorry for the long answer. Hopefully, I give you some color into the problem.
Fantastic. Thank you for that, Pablo. I want to thank our guest panelists as well as all of our host panelists for helping us put together a fantastic first event of 2023. I want to wish everybody a happy new year, and I hope to see all of you for our next Python event. Now, do note that the recording of this event will be available shortly. We'll be emailing you once it is posted on our website. And I would love to see each and every one of you for our next event, which will be on the 22nd of February, featuring, I believe, the fine folks from Tut Institute talking about projects like UMAP and so on. Now, Leland McInnes and John Healy. Thank you for all of your fantastic questions as well as the fantastic comments. I hope you all enjoyed this event, and I'll see all of you next time.